At this point during our lecture, you should be able to collect the data and present it into a table of data. You should understand which information you have to include in the raw data and which you don't have to. Now let's move on to the next big topic, which is data processing. When it comes to data processing, the first thing that we usually do is to calculate the mean, or the average of the values. The mean is just a statistical terminology for the arithmetic average, and this is equal to the sum of data values divided by the number of data. For the purpose of the presentation, we will demonstrate the sample calculation only on the first row of the data. Looking at this raw data, we can calculate the average time t, or the mean t, by summing all of the 4 measurements of t, and we divide by 4. The mean t for the first row here is 0.32. We now want to extend the notion of uncertainty into a set of measurements. The measurement uncertainty of time is 0.01 seconds, but the actual uncertainty here is greater than 0.01, as demonstrated by the spread of the data. Look, for example, the first 2 trials. The difference is 0.1. This is 10 times larger than the measurement uncertainty. Therefore, we should use a different method to determine uncertainty in data values in order to better describe it. Experiments show that when we conduct many trials and collect a large number of data, the distribution of the data will take a symmetrical shape known as a normal distribution. The center of the shape is called the mean or the average. The majority of the values are slightly higher or lower than the mean, and only a few which are significantly higher or lower. In addition to the mean, we have this symbol sigma, which we call a standard deviation. This may sound complicated, but this number square is just the average of how each data differs from the mean value. Therefore, a standard deviation sigma is a good measure of the width of the distribution, or the uncertainty of the distribution. This is simply the uncertainty associated with a set of measurements or data values. And sigma is given by this formula. However, we will not be using this formula in this course. Instead, we will use an approximation to quickly compute it, and of course, the approach that is accepted by IB. In this course, more often than not, we will collect the data with no more than 10 trials, and that's not enough to get a normal distribution. For that reason, we will use the following approximation. According to mathematical probability theory, approximately 68% of normally distributed measurements fall between one standard deviation on either side of the mean. That means the range of the data is between minus sigma and plus sigma. In this approximation, the range, which is the difference between the largest and the smallest data values, can be written as mean plus sigma minus mean minus sigma. As a result, the range is 2 sigma, or 2 standard deviations. From this, the standard deviation sigma is equal to range over 2. And since the standard deviation is a measure of the width or the uncertainty, we will use this relation to calculate the uncertainty of data values throughout the course. Let us calculate the uncertainty in t, or delta t, by using this relation, range divided by 2. The range is the difference between the maximum t and the minimum t. The maximum time from the raw data is 0.37, and the minimum is 0.27. We take the difference and divide by 2, and this is equal to 0.05. So the uncertainty in t is plus minus 0.05 seconds. Last time, we outlined this relation, d equals 1/2 gt squared. Since this relates the distance d and the square of the time t squared, in this table we will also calculate the mean t squared and its uncertainty. The mean t-square is calculated by squaring the mean t, which is in this case 0.32 squared. The result is 0.1024. But remember, you square a number, you multiply a number by itself, and using the concept of significant figure, the result should be written in two significant figures. So in two significant figures, this number is written as mean t-square equals 0.10. Now the uncertainty in t-square. The uncertainty is calculated in the same way as before, range over 2. You can also use the approximation we discussed before about propagating uncertainties. But this approach shown here is nice and quick, range over 2. The range is maximum t-square minus minimum t-square. This difference is divided by 2, and the result is 0.032. As an exam tip, the number of decimal places of the data and the uncertainty should be consistent, and the uncertainty is rounded to one significant figure.